So the last review talk is going to be given by geodynamicist Zhong. Is going to give us a review, and he lost his PowerPoint right before the coffee break. So let's see how much he has recovered. Can show us.
Well, I guess Cindy must have said something really shocking. Actually, as I was saving my PowerPoint, it just crashed, and I could never recover. And so I missed your talk, and I also missed Zhong's talk as a result of that. And actually, the truth is, I've been working on this I actually not been working on this geothermal kind of problems for quite a while. So I started with a relatively old PowerPoint, about more than 10 years old, and I opened it and I started working on that for the last couple of days, and it's not savable. And I tried to save, and so anyway, that's a mistake. And I guess I shared office with Jay, and last Friday she asked me. She said he needs somebody to cover the geodynamics point of view on this issue, and I kind of casually said, "Oh, maybe I can do it." And it turns out that actually it was a lot of work. And actually, as I prepared for this, it kind of reminded me that, in geodynamics, I guess that's why probably Peter Olsen and Bruce Buffet all turned down. And I guess, as geodynamics, we don't really study geotherms, and we study processes, and so physical processes. So, and the temperature actually will come up as a result of that. Okay, so what actually you'll see that from my presentation is actually I will try to really put this in different kind of physical processes. Okay, so you'll see the temperature and the geotherm actually will be essentially the outcome of that. And also actually Lars of course gave a wonderful talk, and I was sitting there feel like, oh, maybe actually probably it's okay that I actually don't give this talk. Anyway. That's right. I shouldn't really. I actually can see if I can get this to work. Okay. Yeah, this actually works. Good. So I will start from shallow to deep, and most of course about the mantle. And so I'll start with the lithosphere, and then we'll talk about the convective mantle. Then I'll talk about the core mantle boundary regions. Okay. So for the lithosphere, of course, if we talk about the temperature geotherms, we have to really rely on some sort of observations, and the heat flow is naturally very, very useful, and we really we can measure the heat flow. We have very good reason that temperature gradients, at least in the lithosphere, should be more or less remain somewhat constant, unless you in the continental regions where you have a lot of radiogenic heating that actually can modify the temperature gradients. Okay, but in any way, the heat flow is very important information we have here, and also the bathymetry. Okay, and so actually I'll tell you a little bit about why this is relevant. So this is all relatively old topic, and if you actually take the heat flow from the ocean and you kind of do the average. You plot against the edge of the seafloor, and you typically see this squarish. There are some uncertainties, but largely this is the kind of the pattern you see. Okay, and you look at the ocean depths, and this is again, plot ocean depths against the edge, and this is the dots that are actually roughly what you see. Okay, and so the ocean depth increases with age, and the heat flow actually decreases with age. Okay, this is all well known, and then of course. A model, really old model, and a half-space cooling model that actually been proposed to really account for the heat flow observation and the bathymetry. Okay, I'll just very quickly kind of review this a little bit. And so what you can actually see here is you can consider column of uniformly hot material at the spreading center. Okay, with some temperature throughout the mantle temperature. Then of course the plate motion will carry that column of hot material away from the spreading center, and as that column moves away from the spreading center, actually will start to cool from surface because surface temperature is very low, and so over time you actually develop a thermal boundary layer, and the boundary layer thickness little delta actually scale with square root of kappa t, and the kappa thermal diffusivity t is the h, and so. And the solution is actually, you can, from Turka-Schubert, it's a sort of typical, place you can actually find. This is very simple stuff. And this is the temperature actually is given by this error function, is well known. And heat flow actually can be computed analytically. Oh, by the way, there's a pi here I missed in the denominator there. And so this is the heat flow, and this actually can also compute the bathymetry. It's all well known. And then this is essentially what you actually see here, okay? And this is line here actually is a prediction from the half-space-Cooney model, and this dashed line is actually the prediction from the half-space-Cooney model. And to a good, I guess to some good degree that really the half-space-Cooney models actually explain observation fairly well, okay? Except at the relatively large depths for heat flow, the heat flow tends to be higher than the prediction from the half-space-Cooney model. And again, the bathymetry, of course, appears to be flattened at about 80 million years, okay? And again, it's all well known. And then here comes a play model. In order to account for this flattening in bathymetry and apparently heat flow, people like, I guess Parsons and others actually, they propose there might be actually some kind of, plate, and that is actually this temperature, or say, in these columns, they will not, they actually will not cool indefinitely. Rather, there is some kind of asymptotic thickness for this plate, and then beyond that, the temperature will remain the same. Okay. And so this is essentially the play model. And you can solve this. There are solutions, the kind of complicated solutions. And then the solution is complicated, but actually can fit the data. Okay. Well, if you say, okay, that's all I want, then this is the end of the story. And then, of course, we know, as Lars actually mentioned, the play model is the empirical model. Okay. It's a curve fitting in some way, right? And of course, McKenzie, Parsons are really, the outstanding scientists. They certainly, fully appreciate that. They're aware of that problems. They actually come up with this idea of the small-scale, sublithospherical small-scale convection as a mechanism to really, for this play model, right? And so the idea is that as the boundary layer thickens, and if you somehow define a Rayleigh number or local Rayleigh number, and as you can see, the little delta here is actually cubed in this Rayleigh number definition. And so as the delta increases, somehow the Rayleigh number actually will increase, and eventually will be bigger than some kind of critical Rayleigh number. Then the convection will start. Okay, so that convection actually may somehow give you this play model, and that's actually the hope, right? But then really they have never really demonstrated that. So actually, I'll show you some studies this has been done for some years ago. And this is a two-dimensional calculation, and with temperature-dependent viscosity and all that, try to really simulate this process of small-scale convection. So what you actually can see is that maybe the plane motion, just imagine the plane motion is towards you. So we actually cut a cross-section perpendicular to plane motion, and so. So what you actually see here, this is the heat flow versus the time. And this is actually what I have plotting here. It's a horizontally average temperature versus depth, okay? So there are two lines here. The solid line is actually numerical results, model results. The dashed line is a half-space-Cooney model, okay? And so you can see, small-scale convection start. And at this point, you start to see deviations for the temperature structure between the model results and the half-space-Cooney models, okay? Right? And the numerical results with the small-scale convection tends to give you hotter lithosphere. So the solid line, is above the dashed line. Dashed line is half-space-Cooney model, okay? If you look at, let's actually look at this again. So everything agrees well perfectly with a half-space-Cooney model. Now the small-scale convection start. Okay, you start to see essentially heating up of the lithosphere. Okay, so the lithosphere is hotter than the half-space-Cooney model, right? And the heat flow is larger than the prediction from half-space-Cooney model. This actually appears to work, right? It's just you have enhanced the heat flow once small-scale convection starts, and the lithosphere is actually hotter than the Hofstadter-Cooney model predict once the small-scale convection start. But actually, I want to point out to you that if you actually look at the mantle at a relatively large depths, this actually will come not free. Okay, so you heat up the lithosphere, you remove the relatively cold material from the base of the lithosphere, and that cold material actually will sink into the mantle, and you actually cool the mantle. That's actually what you see here, right? The dashed line is actually, sort of more or less scale. That's scale one. So what you actually see is here essentially is a vertical heat change. Okay, so you removed the cold material from the base of the lithosphere, you dump that into the mantle interior, and you cool the mantle. I remember the play model assumes that basically below the play depth, say 100 kilometer, the mantle is isothermal, okay? And somehow due to the small-scale convection effect, right? And so, well, it's clearly you see the mantle actually is cooled, right? So, actually, this is actually really Rick. Rick actually, and Hager actually, published this. Really shortly after McKenzie proposed this idea, then Rick actually made an excellent point. And he was actually, he envisioned this. He said, well, you have small-scale convection that removes the bottom part of this sphere, the cold, you dump that in the interior, that actually will affect the bathymetry. So he actually suggests that this vertical exchange of heat from small-scale convection may actually cause deepening, not flattening of the ocean depths, okay? So, of course, as I said, this could account to heat flow observation reasonably well. Let's actually look, let's look at the heat, the bathymetry calculations from this kind of model, okay? So this is actually, we have a very long box. You can actually see this, maybe consider this as a Pacific plate. You see the small-scale convections. There's a big circulation going on here, okay? So we have small-scale convection, and of course, models like this, you really have to quantify results to learn anything, okay? So what we actually, what we have done here is that this is the horizontal, positions, and we actually over each, say, every dimensionless distance of, say, 1, we actually kind of do a horizontal average of temperature profiles. So that's actually what you see, the solid lines at the different locations, okay? And the dashed line here actually just, Hofstadter-Cooney model, okay? So we know the age at the surface, so we can actually take Hofstadter-Cooney models, we plot at each locations, and then we also quantify the numerical results in the models in the same way. We plot together. As you can see, the small-scale convection certainly, hits the lithosphere, so the solid line is above the dashed line, and you see that all the way, okay? And in the mantle, because of small-scale convection, it's somewhat, somewhat actually, more or less homogeneous temperatures, okay? But you also see near the base, there because of the convective return flow, and you actually start to see some, significant deviations, okay? Of course, that's because in this case, it's actually return flow. Lars mentioned about the sub-adiabatic temperature. I'm going to actually get there. In some way, you can sort of see this, right? If you have mantle convection, and all this fluid field, of course, it can actually cause a deviation from this simple, sort of adiabat, okay? Although this is actually the Boussinesq calculation with no adiabatic gradients, but that's sort of where where you can actually see. Now let's look at the bathymetry, okay? Yeah.
At what age, what's the equivalent in the plane where the small-scale convection becomes important?
Yeah, there are a lot of studies actually on this onset time. You actually, in our models, we can actually adjust the parameters to get whatever age we want. And so I guess in this case, probably, I cannot see, let's see, this will be 6, let's say if the whole mantle, this is 6,000. So I would say this is probably, around 80 million years-ish. Yeah. So, there's this is 8 centimeter per year. And so, yeah. So anyway, now let's actually look at the bathymetry, right? So this is our model. The solid line is the model prediction for the bathymetry, and the dashed line is Hofstadter-Cooney model. So you got all the things that you want for the play model. It looks like, well, you certainly don't see a very nice flattening, okay, as what you want for the play model, okay. But it's not Hofstadter-Cooney model either, okay. And so this kind of tells you that there's the complexity of the problem. So anyway, this is for 2D models. This is actually for we can do the same thing for 3D models. Now you start to see the rickroll. This is 3D. You look at the map view, and you start to see this the convective rolls actually lined by along the plane motion. The general idea actually is quite similar to what actually I present you already in the 2D models. Okay, so I guess a quick summary about the geotherms for the lithosphere. For the oceanic lithosphere, I would say there's a plane model and the half-size cooling model. They're really two end members. Okay. And the truth is probably somewhere in between, okay? And so depending on what you want to study, you can pick. I think for most problems, the half-size cooling model or plane model probably is okay for you, okay? But for some certain other problems, actually the difference between these two, of course, actually is it's tremendously important. For example, if we care about dynamic topography, what the reference model you use is actually giving you a big difference, okay? And so I guess so far people often actually either use they use either plane model or half-size cooling model as a reference to subtract the bathymetry topography out to get this so-called residual topography. As I showed, it's not that simple, okay? And maybe these two again, the residual topography inferred from either subtracting out the plane model or half-size cooling model. Again, those are probably just two end member cases, okay? So that's actually the kind of summary note on this on the oceanic lithosphere issue. For continental lithosphere, synthesis here, I'm not going to say anything. Okay, he already talked about it, but I missed the so now the convective mantle. Lars already talked about this. Largely, the mantle for the convective mantle, the geotherm follows adiabatic. Okay, largely. Okay. And so this is sort of, this is the adiabatic gradients, largely follows that, okay? And of course, this is only giving you the gradients, and you still need some reference point or anchor points, right? And this is from, called Japar, things like the morb generation or melting process that provide you some reference temperature or anchor temperature point. And then, of course, the phase change, they're very useful. The melting temperature at the core mantle boundary. This is all very, very useful anchor point for actually for us to be able to pin down the temperature of the geotherm and give then together with this grade the adiabatic gradients. Okay. Then of course you have this is very similar to Lars what Lars showed. And there's a phase change here. Okay. The 410, 670 and I guess 520 there, okay? So a little bit on this subadiabatic temperatures. I guess Lars already mentioned about the, really the number, I kind of put the numbers here. Actually, if you read the journal Maurice 87 paper, it actually really said 400 to 500 Kelvin, not 200 Kelvins. And Peter actually, I guess, was not very clear about this. And I would actually, this is the depth, I should say. And this is the core mantle boundary on this side. I mean, he somehow in this paper, he also kind of suggests, maybe you'll get a 400 Kelvin subadiabatic temperature, okay? And so that's, so we actually, of course, as I said, we never really study the geotherm problems, per se, and rather we always study some physical process, and then the geotherm just kind of output. Okay, so now this is actually, I want to show you some study we did for mantle plume dynamics. Okay, I know there's a Plume group. I don't know whether we have any students here for that group, from that group. And so anyway, so in this problem, we're really kind of interested in the Plume dynamics, okay? And then we formulated this, the compressible mantle convection models, and this is three-dimensional, the temperature-dependent viscosity, et cetera, et cetera. And so then in this case, we run our model to quasi-static state. So as you can see, this is time, the heat flow, core mantle boundary heat flow, and the surface heat flow, and this is got a mixed internal heating and also basal heating from the core. Okay, and so I guess in this case it's about 50% internal heating. Okay, and so you see plumes coming up, and because there's a depth-dependent viscosity with relatively weak upper mantles, you see the plume, width actually shrinks when the as the plume get to the up mantle, and this is down warnings and all that. Okay, So of course we have to quantify the models very carefully and not just seeing color pictures. And so here what I actually showed you is a radius, okay, non-dimensional radius versus the temperature. And this is actually, so the solid line here is actually horizontally average temperature from the model, okay? And so you see the adiabatic gradients, and there's actually, because we also got a phase change there, and so you see this bump in temperatures, okay? Then I also, what I have here, the dotted line actually is the adiabatic temperature, okay? And so all I did here essentially just to integrate that equation, the adiabatic gradients. I start from, say, up mantle, somewhere outside 200 kilometer depth. You start from that temperature, I just integrate down the slope. Okay, I kind of ignore, when I actually computed the adiabatic temperature gradient, I ignore the phase change. So that's why you didn't see this bump there, okay? But overall, you can sort of see there are some differences between the average temperature from the mantle, from convective mantle, and the prediction from this very simple, right, the adiabat, okay? And so this is actually what we call the subadiabatic temperature, right? So I would say the subadiabatic temperature is relatively small, non-dimensional sense. It's about, for most models, it's about 0.05. Then if you assume the core mantle boundary temperature is 4,000 Kelvin, then this means that the subadiabatic temperature at the max is less than 200 Kelvin. Okay, that's what we've seen. We actually run many models, 20, maybe 40 different models with different internal heating, and this is about, many cases actually even much less than, this, okay? So I don't know how significant this is actually to seismology. To geodynamics, we mostly don't care, much about it, okay? That's why you don't see many papers from geodynamics saying subadiabatic temperature. It's just not very significant. If you think this may be significant for interpreting seismic results, well, then we can actually then, maybe you should tell us, then we can actually study this in great details, okay? Now, what I'm actually showing here is actually, this is the Plume temperature, okay, from the model, right? You just go to quantify the Plume models. And so you can see, this is just like what Lars said earlier, right? The Plume temperature actually follows different adiabat, its own adiabat, because if you recall, if you recall, the adiabatic gradient is actually proportional to temperature. So for Plume that is hot, then actually the adiabatic gradient tends to be larger. That's essentially what you see. This is directly from our models. And actually, I didn't plot the adiabatic gradients predicted for the Plume, and they really plot like onto each other. Okay, so and then of course, as you can see that, as actually Lars already mentioned this, and if you actually ask about the Plume excess temperature, that is the difference between the Plume temperature and the average mantle temperature. And the Plume excess temperature is much larger in the lower mantle near the core mantle boundary than that in the up mantle. Okay, so this would actually have important influence on Plume heat flux or Plume buoyancy flux, which we actually compute or quantified as well. That's actually, this is again, we normalize the Plume heat flux against by the surface heat flow. Okay, so you sort of see that really the Plume heat flux near the core mantle boundary is actually, in this case, is about 3 times larger than the up mantle Plume heat flux. Okay. Then I guess, of course, you actually can use this to really place constraints on internal heating rate or the core mantle boundary heat flux. Okay. So that's essentially what we did, and actually, I just want to kind of quickly go through this a little bit with you. And so the Plumes actually, they're complicated, but really they really contain a lot of useful information. Okay, so we know the up mantle temperature, or you can say probably around 1,300 degrees Celsius. Okay, that's up mantle, maybe 200, 300 kilometer depths. Okay, and then the core mantle boundary temperature, of course, is a bit of there's quite a bit of uncertainty. I'll just put some uncertainties there. And then, of course, if you take this together, you sort of say, okay, that means the normalized temperature of up mantle to the core mantle boundary temperature will actually be in this range. Okay, so that's one thing that we know reasonably well. Then the Plume excess temperature is typically on this order. This is typically we're talking about the Plume excess temperature derived from melting, so this has to be for the up mantle, right? And so which means that then you take this temperature plume excess temperature in the upper mantle, you normalize by the upper mantle background temperature, you get this, this ratio there. Okay, that's to a large extent, this actually is reasonably good. Okay, estimate. And now, all the plume heat flux. Okay, so the plume heat flux, it's actually really derived from the plane motion and the swell topography, as Davis and Sleep, did many years ago. So back then, the Davis, Sleep, they sort of said that okay, the plume heat flux actually accounts for about 10% of the surface heat flux. And back then, they actually argued that the plume heat flux will just really represent the core mantle boundary heat flux, and therefore, mantle convection is largely interheated. 90% is interheated. Okay, so this is like 20 years ago, that actually was really the main idea. Okay, and this is people talking about a 90% interheated convection. This is essentially where it comes, where it actually was from. Okay, this is of course, as I showed you earlier, if you start to consider the fact that the plumes actually follow different adiabat, and the plume heat flow in the lower mantle can be potentially much larger than the plume heat flux in the upper mantle, then we really have to revise this idea, right? So we've been running a lot of models. Again, this has been published, more than 10 years ago. That's why my PowerPoint crashed. So what I'm actually showing you here, this is actually calculations, showing in the horizontal axis is actually into the heating rate. So this is the 10% into the heating. That's 80% of into the heating. And then the vertical axis here, in this case, actually this is the plume heat flux in the upper mantle. Okay, so we know this shaded region is more or less observed range that I mentioned, inferred from Davis and the Sleep. Okay, that's about 10% ish. Okay, and so as you can see, as you actually increase into the heating rate, and the plumes tend to get weaker. Okay, so therefore plume heat flux actually is reduced, and so you sort of see this trend. Okay, and so by the time you get to about 70% into the heating for the mantle convection, then this number actually model prediction gets to be kind of consistent with observed. Okay, with inferred, right? And now this one actually is a plume excess temperature for the upper mantle that I already mentioned to you, and so this is the observed range. And then the model results again consistently shows that you need to have about 70% into the heating, and to get you to give you correct plume excess temperature in the upper mantle. Again, this is actually the upper mantle temperature, non-dimension normalized by the core mantle boundary temperature. And this is actually because of the big uncertainty for the core mantle boundary temperature. Then this is actually the range is much larger. But overall, if you have 70 or 60% into the heating, and this actually would also be consistent with observation. Interestingly, the plume temperature in the upper mantle is more or less constant, okay, from our models. And as you can see, because the plumes actually derived from the core mantle boundary, so the temperature is less affected by whatever going on in the internal heatings, okay? And so if this is true, that means the core mantle boundary heat flow is about, say, 30% of the surface heat flow. And we know the surface heat flow is about 36 terawatts for the convective part. So which means that the CMB heat flux will be on the order of 10 terawatts, okay? I remember Jeff Davis, Norm Sleep actually used to say this is about 3 terawatts. And then that actually ran into a lot of problems with the dynamo community. And the dynamo community actually was it's much happier with the 10 terawatts, okay? And so anyway, this is the number that we have. What do we have here? Okay, summary on the, I guess I'm supposed to talk about geotherms. So I would say that, the geotherm in the mantle, in the convective mantle, follow adiabat largely with about less than 200 Kelvin sub-adiabatic temperature in the lower mantle, okay? And a plume actually would follow its own adiabat, okay, with a steeper slope. If you want to ask me about the slabs, we can talk about that. It's very complicated. And we tried for 10 years. We couldn't really understand what's going on with the slab, even with very simple models. And I emailed my former student, Wei-Nen, and last slide, I said, what happened? I know actually he's been working on that slab, geotherm. very simple models. Apparently it doesn't follow Adibet, okay? We don't have good models for that. And he emailed me back. He said his paper just got rejected by Geophysical Journal International on this slab geotherm issues. Not sure really what happened. And so now the geotherm in the CMB region. I guess I actually use this. And so this is a CMB region, right? This is a thermal boundary layer. And so whenever you have a thermal boundary layer, and the geotherm is kind of complicated to infer geotherm. And we need, of course, the temperature anchors, say from melting or phase change to help us to pin down the geotherm there. And post-perovskite phase change, that of course is a great help. Then anything related to heat flow, just like for the surface, right? To get the geotherm for the surface boundary layer, and we need heat flow. And at the core mantle boundary, if you have heat flow information, that will be very, very useful. The things like I showed you, the Plume heat flux, and I think it actually is quite useful to constrain the geotherm near the CMB region, and the dynamo constraints or post-perovskite, and they're all very, very useful. And then of course, this is actually from Zhong's paper, and this is the post-perovskite, has been discussed already, and I'm not going to say anything there. And I'll say that, of course, Dan Shen actually just asked this. I think it's also very, very important. That is really, this is the global, the post-perovskite phase change. This is global or not? I mean, it looks like it may not be a global feature, and so if that's the case, so if that's the case, really we have to worry about how to constrain the geotherms in regions without post-perovskite. Okay, so just want to end with the final slides here. That is what happened with the thermochemical convection, right? We've been talking about a lot about the chemical powers, et cetera, et cetera. That provides another layer of complication here. And so what I'm actually showing you here is just layered convection. So the bottom layer is more dense. In this case, actually really dense. You have almost like a two-layer convection. So what you see here is the composition, and this is actually the thermal structure, largely from the top layer. Okay, and so you still have down warnings and up warnings, but that's really only for the top layer, and the bottom layer kind of convex separately. Okay, because of the heavy composition for the bottom layer. And so now you see, this is actually, again, horizontally averaged temperature and composition, the dotted line is composition. So very different, distinct composition right from the bottom layer. And now you got another boundary layer there, okay, thermal boundary layer. And of course, there's actually conductive heat out from this bottom layer to top. Okay, that's why you have a thermal boundary layer. So you have a thermal boundary layer. And you need, as I said, you need some information to infer the geotherm. You need either some kind of temperature, marker or anchors, or some heat flow. And I guess we all know this is very, very difficult to get any information about this layer. So if you this thermal boundary layer, right? Now that's actually relatively simple thermochemical convection, because really it's just more largely two-layer convection. Now, if you think about thermochemical powers, there are certain places you have this thermochemical power, right? And that's, it's going to be even more complicated. So, well, it's kind of hard to really, I guess I don't really have any conclusion slides because, anyway, I would say, it's not easy, it's not an easy project. It's a process, I guess it's really a process specific, right? Yeah, thank you. Yeah.
Thank you, Shijie, for a great talk, especially at such short notice. We have 15 minutes before lunch to have a general discussion. Any question related to this talk or any talk in the morning?
So this is it's a somewhat general question in a way. So you talked about the constraints from the Plume heat flux, and we also saw some sort of discussion about the temperature gradients and so forth within the LLSVPs, and you might be able to nail them down. Can we tie together a little bit about whether or not the LLSVPs have their own internal heating. That seemed to be a sort of a conversation and what that implies for the heat flow from the core versus the core heat flux, and also what it means in terms of the double crossing gradient constraints. I mean, that seems quite confusing to me.
Yes, actually, the reason that we're actually we did this, two-layer model, thermochemical models, was really try to ask the question that is how much radiogenic heating you can put in the bottom there. And, there's a lot of geochemists like, put a lot of radiogenic heating in the bottom there. So if I think there are certain degrees, to which you can do this. And if you actually put a lot of more radiogenic heating in the bottom there, in this, I guess maybe in the chemical pile, then the plumes actually will be generated from this piles. Then for the mantle above, then it's largely basal heating convection again. And so that actually will violate, I think in my own view, it actually will violate maybe the plume constraints again. So I think, why? If you actually, I guess maybe I'll see, that's the wrong direction. Okay, here. So as you can see, so if you have more like a basal heating convection towards this end, this is very small internal heating, then the plumes actually tends to be really strong.
Okay, so this is
Yeah.
my opportunity to ask the question I've always, a naive question that
Yeah.
I've always wanted to ask is, how do you know that, by looking at calculating the heat coming from each hotspot, you really have all of the heat accounted for by quote-unquote plumes coming from one and another?
Well, that's I guess if you look at most of our models, you see the plumes actually they tend to be rather continuous process. So they form and the small ones they can never make to the surface anyway. So really only the relatively large plumes they actually can carry the heat out. And so in our model calculation, we basically just go after this this top 10 plumes. They transfer the most heat out. And
right,
so,
but how about if there is more heat coming out in the lower mantle in plume-like structures that some of it gets deflected towards ridges under the lithosphere? And
that's
so
possible. We actually in the models we actually quantify the plume heat flux from the the lower mantle all the way to up mantle. So that actually and so probably before the plumes got sucked into the mid-ocean ridge. So in a way we didn't really miss that.
but it's a very specific plume model that you have.
That's true. Yeah, that's true. Yeah, it is yeah, that's true. I think overall there's always this in my own looking at our models, which is basically numerical models, whereas then look at the seismic models. The seismic models plumes tend to be really large. I remember Hussein actually, right, did some calculations of plume flux, and he got us outrageous numbers for plume heat flux. We know it cannot be physically possible. So I think how to really bring the seismic plumes together with the geodynamic plumes, I think it's going to be useful, interesting exercise. And the answer is probably not very simple because I think seismic plumes tends to be just too big as far as we can if you just look at the published models.
Yeah, but they may be too big. But if they were smaller, we wouldn't see them.
That's true. That's I guess that's really the kind of puzzling part of this. Yeah.
But I think it's fair to say, right, that the estimates from the geodynamic models, or I think if you use the surface, just reaching the surface has to be a lower bound, right, on the CMB heat flux. Okay?
Yes.
I think
Yeah.
it has to be a lower, well, maybe not quite the lower
Yeah.
bound, but very close to that, because you're missing plumes that don't make it, right?
Yes. I mean, I guess I would also say a lot of the small plumes they coalesce together, then form bigger one, they eventually make it. So a lot of many plumes actually just simply disappear, and we don't see many of those. Yeah.
So I wanted to bring up more of a general point. You very politely
That's a good question, yeah.
You should answer that.
A 4D geotherm with the time evolution. But for mineral physicists especially, we definitely need a reference because when we have experimental data, we want to connect it to seismic observations. We need a reference temperature profile or distribution in order to go forward. So for that, I think the need is definitely there. Maybe, yeah, from a geodynamics point of view, you guys are putting in things, but you don't care about what comes out, right? So you don't need the input of geotherm, but you can produce some constraints.
It's more the point that you reference geotherm for mineral physics. Why? Because there's going to be a different composition, a different dynamical process. So, what are you going to use 15 different geotherms in your mineral physics then to compare to a particular seismic observation? I mean, what are you going to do?
I think to be aware of the variation, how the geotherm, the temperature profile vary with location and temperature is going to be very helpful. For instance, the examples I gave, we want to know whether carbonate is going to melt at transition zone, whether silicate or metallic composition is going to melt at a core mantle boundary, whether you have the snowing and process going on at the inner core boundary. We need something in order to do inference. So if you say, oh, the variation is so large that this is a possibility, or maybe it can be excluded even within the uncertainty. Or maybe you say it's not happening right now, but it could be in the past or in the future. So we still need some kind of a reference. Because every time after project, I'm looking for some sort of reference geotherms in the literature.
It seems that the first order thing still is the potential temperature underneath the ridges. And this, I like the delta T. I mean, you may not know Q. That's you don't know all the plumes that make it to the surface. But if you can get delta T now, if we can ever resolve that, and in the past, then you already learned a lot. Right? And then on top of that, there's the variation. You have to get this first.
I mean, if anything, just maybe some kind of review would still be useful.
Yeah, the understanding, for instance, I learned a tremendous amount from the review talks this morning. I hope some other people also had the feeling. So we now know the complexity and then what to consider instead of having simple-minded geotherm to use to interpret our data. So we could be more sophisticated and more realistic by having this. So it's not going to be just a profile, but really a paper and a resource that includes the references. And we can think about the Earth in a more dynamic and a more sophisticated way. Okay, so Huang has something.
Well, we should probably go to lunch, but I was curious, for plumes originating from the thermochemical boundary, they're not sampling core mantle boundary temperatures. They're going to be a much lower temperature. Have you gone through this exercise to calculate their melting temperature excess and get a total integrated plume flux for something that's realistic?
Yeah, well, realistic. That's a question. Yeah, we actually tried this, relatively large buoyancy number. So it's more like a two-layer systems with very little oscillation for the composition of the boundary. That actually we carefully quantify the plumes and all that. But for the chemical pulse, those are actually hard to do. I guess the reason is actually the chemical pulse. Once you start to have them oscillate, typically in the model that we're doing, and the entrainment is tremendous. We just cannot run for long enough, to do so we can do statistical. Because then so quickly got entrained. So yeah, that part we haven't done. But for the more like a two-layer systems, actually, I guess this paper was quite a bit of, there are a lot of actually on the two-layer systems. One conclusion I remember was really the bottom layer. You cannot put too much radiogenic heating in the bottom layer because otherwise the top layer will appear to be basal heating convection again. Then the plumes will be too strong. Yeah.
So I guess asking the silly question of reference geotherms, is also a way to get people think about these issues. And given the time, I would like to mention that we have the afternoon session starting at 2 o'clock. It's going to be a short session, only an hour and 15 minutes, just before the coffee break. And what we are going to do is to look at Earth and divide it into different layers and try to integrate all these constraints. And ask the question, what do we want to have if we want to propose a reference to geotherm? What kind of information do we want to get there? What are the key constraints? So we have some kind of a roadmap to go forward in terms of producing this online resource and writing this review paper. So I strongly encourage all of you guys to come over to join the discussion. So the success critically depending on your participation. At this point, let's thank all the speakers who gave us excellent reviews. See you at 2 o'clock in the afternoon.